Perched like small caps above your kidneys, there are two glands that rarely draw attention. Until the moment everything changes. Until stress hits. Until danger appears. Until your body must decide, within seconds, whether to stand your ground or run for survival. Because in that instant, a decision is made not in your mind, but in a structure no larger than a walnut. The adrenal glands. Small, hidden, but absolutely central to survival. Why would evolution place such a critical command center on top of the kidneys? And how can such a small organ control heart rate, blood pressure, metabolism, immune activity, and even long-term stress adaptation? The answer lies in a division of labor so precise that it effectively separates survival into two biochemical worlds: the adrenal cortex and the adrenal medulla, two distinct systems, two different timelines, one built for immediate action, the other for sustained endurance. And together they define how your body responds to stress. The adrenal medulla sits at the core of the gland. It is neurologically connected to the sympathetic nervous system. In fact, it behaves almost like an extension of it. When your brain detects danger, sensory regions process the threat within milliseconds. The amygdala evaluates emotional relevance. The hypothalamus activates autonomic output, and sympathetic neurons fire instantly. Signals travel down the spinal cord and directly activate chromaffin cells in the adrenal medulla. Within seconds, these cells release powerful catecholamines into the bloodstream. Adrenaline and noradrenaline. These molecules do not act slowly. They act immediately. Heart rate increases, stroke volume increases, bronchial tubes dilate. Blood vessels in the skin and digestive system constrict. Blood is redirected toward skeletal muscle. Glucose floods the bloodstream through glycogen breakdown in the liver. Fat stores begin mobilizing fatty acids as alternative fuel. Pupils widen, attention narrows, reaction time sharpens, and even pain perception is partially suppressed. This is not a single reaction. It is a coordinated whole-body metabolic reconfiguration, a system designed not for comfort, but for survival under extreme time pressure. There's no interpretation layer, no deliberation, only execution. But if stress continues beyond seconds, another system takes over. The adrenal cortex is the outer layer of the gland, not neural, but endocrine, and operating on a completely different biological timescale. Instead of instant release, it synthesizes steroid hormones through enzymatic pathways derived from cholesterol. This process takes minutes, not seconds, but produces longer-lasting systemic effects. The most important of these is cortisol. Cortisol is not about immediate survival. It is about sustained adaptation. It ensures that if the threat does not disappear, your body can continue functioning under pressure. It regulates glucose metabolism, immune activity, inflammation, vascular tone, and long-term energy allocation. It reshapes physiology over minutes, hours, and days. This is controlled through the hypothalamic pituitary adrenal axis, a hierarchical feedback loop connecting brain perception to hormonal output. The hypothalamus releases corticotropin-releasing hormone. The pituitary responds with ACTH. The adrenal cortex responds with cortisol, and cortisol feeds back to both brain and pituitary to regulate further release. A closed-loop control system, but not static, oscillating, following circadian rhythm architecture, with peak secretion in early morning, gradual decline throughout the day, and suppression during sleep to allow tissue recovery. However, stress can override this rhythm. Repeated activation distorts the baseline curve, and when this happens chronically, the entire endocrine profile begins to shift. At the cellular level, cortisol binds to intracellular glucocorticoid receptors. These receptors act as transcription factors, meaning cortisol does not just change function. It changes gene expression and it determines which proteins are synthesized, which enzymes are active, and how cells allocate energy resources. In immune tissue, this suppresses inflammatory cytokine production, reducing overreaction during acute stress. But chronically, it can reduce immune responsiveness and delay tissue repair. In the liver, it increases gluconeogenesis, raising blood glucose availability. But long-term elevation can contribute to metabolic dysregulation. In muscle tissue, it promotes protein breakdown to supply amino acids for energy production. And in the brain, particularly the hippocampus, it influences memory encoding and emotional regulation. All of this is coordinated through receptor density, feedback sensitivity, and intracellular signaling cascades, which themselves are plastic. They adapt based on exposure history. Meanwhile, the adrenal cortex also produces another essential hormone, aldosterone. This one is part of the renin-angiotensin-aldosterone system, a completely different regulatory axis, triggered not by stress perception but by blood pressure and sodium concentration. Aldosterone acts on the kidneys at the level of the distal tubules, increasing sodium reabsorption. Water follows sodium, so blood volume increases, and blood pressure stabilizes. Potassium is excreted to maintain electrochemical balance. Without this system, even minor fluid shifts would destabilize circulation. Meaning, the adrenal glands are not only stress regulators, they are also long-term controllers of vascular stability. At the structural level, the adrenal cortex is divided into 3 zones, each genetically programmed to produce specific hormones. Zona glomerulosa for aldosterone, zona fasciculata for cortisol, zona reticularis for adrenal androgens that contribute to secondary sexual hormone balance. This zonation is maintained through differential enzyme expression and local signaling gradients, while the medulla remains directly controlled by sympathetic innervation, making the gland a true hybrid organ, neural and endocrine, fast and slow, electrical and chemical. But modern life introduces a mismatch, because this system evolved for short, intense bursts of survival stress, not continuous psychological activation. Chronic stress keeps the HPA axis partially engaged, altering cortisol rhythms, flattening diurnal variation, and shifting baseline metabolic states. Over time, this can lead to receptor desensitization or hypersensitivity depending on tissue type. The system adapts, but not always in ways that improve function. Sleep architecture becomes affected. Deep sleep phases reduce in duration, and recovery processes become less efficient. Even the immune system shifts toward altered inflammatory set points. Not broken, but recalibrated, at a cost. Yet, despite this, the adrenal system continues to function, continuously adjusting output, integrating signals from the nervous system, immune system, and metabolic state, because its primary role is not optimization, it is survival under variable conditions. And that principle remains unchanged. At its core, the adrenal system represents one of the most elegant designs in human biology. A layered stress architecture, immediate neural response, short-term hormonal amplification, long-term metabolic adaptation, all integrated into a structure smaller than a walnut. And perhaps the most important realization is this: every moment of stress you experience is not a single event. It is a full-body molecular transition, coordinated across multiple organ systems, in real time, without awareness, without pause, and without asking permission. Because in biological terms, survival always comes first.